Hello, this is Jeff Hamrick at the University of San Francisco's MSFA program. I want to talk for a couple of minutes about fitting an ARCH or GARCH model to some financial return data using Stata. I'm not going to talk about diagnostic issues for ARCH and GARCH models in this particular screencast. To choose the order of the ARCH specification and the GARCH specification, we use the ARCH-LM test, and we look at the sample autocorrelation function of the squared financial returns or the squared residuals, as the case may be. I discuss those issues in other screencasts. So here I just want to straight up show you how to do the fit. I've got here the returns on the NASDAQ's ETF QQQ. I've created a dummy time variable and declared this to be a time series data set. If I look at time series line plot of these returns, we can see some visual evidence of volatility clustering. For example, we've got kind of low variance here that then spikes and becomes high variance, and then it dies down a bit, and then once again we get higher variance here, and so on and so forth. So an ARCH or a GARCH model might be a pretty good choice in this particular context. So how do we fit an ARCH or a GARCH model in Stata? The command is actually pretty simple. We use, rather than something like regress or REMA, we use ARCH, and I'll name the time series QQQ returns. And let's say we want just an ARCH model of order 3. We want terms of lag 1, lag 2, lag 3. That is, we want to have the variance be modeled by epsilon t minus 1 squared, epsilon t minus 2 squared, and epsilon t minus 3 squared, so on and so forth. This would be the command that I would use. Stata uses numerical maximum likelihood estimation to find the fitted coefficients. And so what do we have here? We've got here the constant associated with returns. That is, the returns are automatically demeaned before the ARCH fit or GARCH fit is done. That's normal. And we've got here the coefficients associated with the 3 lags if we're going to use an ARCH 3 model. The first one is not statistically significant, but the second 2 are. That's kind of weird, but let's go with it for a moment. I think this is probably not an ideal model in this particular circumstance, and this is the constant that I've called alpha naught in class associated with the model for the variance. We would call this guy alpha 1, this guy alpha 2, and this guy alpha 3. That is, this is alpha 1 hat, this is alpha 2 hat, this is alpha 3 hat, okay? And we get approximate 95% confidence intervals for all of those coefficients, okay? As well as associated z statistics and two-sided, two-tailed p-values associated with those test statistics. So this is probably not the best choice. In finance, with financial returns, it's often better to use GARCH 1.1 instead of an ARCH model. So we would fit that type of model by once again using the overall command ARCH. But this time what we would do is we would specify that we want one ARCH term, that is, we're going to model the variances depending on epsilon t minus 1 squared, as well as sigma at time t minus 1 squared. So it adds a kind of recursive element to the variance model. That is, the variance kind of explicitly remembers itself rather than merely being influenced by recent financial returns. So once again, numerical maximum likelihood estimation is used to do the fit. We get a demeaning of the financial return series, and we've got an ARCH coefficient of lag 1 and a GARCH coefficient now associated with lag 1 as well. Remember in class that I said that we will have mean reversion to a variance, that is, or stationarity of the variance itself, if we have the sum of this coefficient and this coefficient being less than 1 in magnitude. We do have that here. That's a good thing. And we also would like, in general, for both ARCH and GARCH models, for these coefficients to be positive. That keeps us away from the possibility that we might somehow end up with a forecasted negative variance, which doesn't make any sense. It doesn't make any sense at all. So just a quick reminder as well, while I'm putting together this screencast, you can have Stata do forecast of the variance. So for example, let's say we're going to go with this GARCH 1.1 model. Let's say I use TS append and I add 10 time periods to this data set. If I then do predict, and let me call my estimated variances my variances, and I use the variance option, Stata will do both an in-sample and out-of-sample forecast of the variances. So we obtain those here as new conditional variances under the GARCH 1.1 model, and it's kind of interesting to take a look at the time series plot of these forecasted both in-sample and out-of-sample variances, because you can kind of see the volatility clustering pretty explicitly. We've got low variances forecast by the model that then spike during that first cluster that we saw. They die down again, and then it spikes up again and dies back down again. So this is what we mean by the phenomenon of volatility clustering or volatility spiking in a financial time series. And Stata, through both ARCH and GARCH models, as well as many models that relate to these two basic models, like the GARCH and mean model, the threshold GARCH model, or the eGARCH model, Stata can help us obtain fits for financial return series if we choose to impose an ARCH or GARCH or related specification to those time series. So that's all for this screencast.